Hello everyone, my name is Javier Avesillas. In this tutorial, we present a welded T-joint that is simulated using the IGL-GFEM GL algorithm with shell-solid coupling between the global and mesoscale problem. The geometry and dimensions of the structure are illustrated in the following figure. And the material properties are Young modulus equals to 2.9 times 10 to the 4 KSI, and Poisson ratio equals 2.3. For this shell solid coupling simulation, the local features to be modeled are the fillet welds and the half circle crack. In this particular case, the plates are connected at the interface between the two plates and through the welds. So in this case, there is no zero thickness seam. As for boundary conditions, the left and right boundaries of the T-joint are fixed in all directions, and the front and back boundaries are free. Finally, the top surface of the vertical plate has a uniform traction of 5 KSI. To summarize, this is a graphic illustration of the problem. On the left, we have the global problem, which is modeled using shell elements. At the middle, we have the mesoscale problem, which is discretized with solid elements. And at the right, we have the local problem, which is discretized with solid elements. So let's proceed with the creation of the models using Abaqus. So first, let's open Abaqus and set the work directory. Now we can create the geometry of the global problem. We have several options. One of them is to create the geometry using the available tools, or you can create the geometry using a CAD software and then import the geometry into Abaqus. So I already created my geometry. And this is how my geometry looks like. I also did some additional partitions that are going to be useful for my mesh generation. Now let's create the material, the assembly, and the step. So let's go to property. It seems like something is missing here. So let's create the material. Mat 1. Mechanical elasticity, elastic. Young modulus. Poisson ratio. Click OK. Create section. This is the shell section. Homogeneous, continue. In this case, the shell thickness is 2. We're going to use mat 1 and 5 thickness integration points. Click OK. And now assign section. Uncheck this option to avoid the creation of unnecessary sets. Let's select the whole model and click Done. Check that everything is correct and click OK. Now let's go to assembly and create instance from the global shell part and click OK. Now go to a step, create a step, insert new step after initial, and this is a static general step. Continue. Let's use the default values and click OK. Now we have to define the boundary conditions of this problem. So we have to fix the left and right edges. So let's create a new boundary condition. Left mechanical displacement rotation, click continue. And let's select the left edges click done, and fix all the DOFs. Let's create a new boundary condition, mechanical displacement rotation. Select the right edge, click done, and fix all these DOFs. Then the front and back edges are free, and we have an applied traction here at the top. Since this is a shell problem, we have to get an equivalent concentrated force, right? So the applied traction was 5 KSI multiplied by the thickness of the shell, which is 2, and then multiply it by this area. We have the value of the concentrated force. In this case, the width of this section is 2 units. So the concentrated force for the interior nodes is equal to 5 KSI times 2 and times 2 again. So let's select the nodes. So create load, let's call it interior mechanical concentrated force. And let's select all the interior nodes. Click done. And let's assign the value 20. Click OK. And let's repeat the process for the exterior nodes. In this case, let's use 10 and click OK. And now we have a set of point loads which are equivalent to the applied traction. Now let's create the mesh. And again, it's worth noting that the user must guarantee conforming meshes at the global meso interface. Okay, so we observe that we have 2 elements here and here. So let's go to the mesh module. First, let's assign the element type. Click done. And we will use linear and uncheck reduce integration. So we will be using an S4 element, a 4-noded shell element. Click OK. And now let's seed the edges before creating the mesh. Well, let's erase all the previous seeds. And now let's select the seeds. So we selected all these edges. Click done. Method by number. And 2. Click OK. Now we have 12 elements along this edge. The same here and here. So again, let's select those edges. Click done. 12. Okay. And finally, we have 15 elements along this direction. But since our original partition already has 15 elements, so we do not need to apply a seed. And this is it. So let's mesh the part. As you can see, we have the same mesh as in the tutorial. Okay, the next step is to go back to the assembly module and select all the global elements that are at the global meso interface, but inside the mesoscale region, and create an element set with the name log interface element. So let's go back to the assembly. Let's show the mesh. And let's create a set, an element set with this name. And now we have to select all the elements. That lie in this region. Then click done. Now select all the global nodes that lie at the global meso interface and create a node set with the name log interface node. So again, let's go to tools, set, create, node. Let's use log interface node, continue. And let's select all these nodes. And let's click on done. Finally, let's create a new job, perform a sanity check, and then write the input file. So let's go to job, create job. Let's use the name global shell, continue. Okay, let's go back to the left menu, right click on the job name and click on data check. So the data check has finished and completed successfully. So let's write the input file, right click on the job name and click on write input. Now, if we go back to the work directory, this is the input file that has all the info of the Abaqus global model. So now let's continue with the mesoscale model. Again, let's open Abaqus, set the work directory. Shell solid, meso solid. Click OK. And again, at this point, we have several options to create the mesoscale model. We can use the Abaqus available tools, or we can create the model in a CAD software and then import the geometry into Abaqus. So I already created my geometry. So let's open the file, and this is the geometry of the mesoscale problem. So repeat step 3 to step 6, which is basically creating the material, the assembly, and the step, and the boundary conditions. So let's create a property. It seems like there is a section here. So let's create the material. Young modulus, Poisson ratio. Click OK. Let's create a section. This is a solid section, homogeneous, continue. OK. And assign the section. Uncheck create set. Select the whole model and click done. Check that everything is in place and click OK. Now let's go to assembly and click on create instance from the mesosolid part and click OK. Now let's create a step. Click on create step. Insert new step after initial, and this is a static general. Continue. Let's use the default values and OK. Finally, let's prescribe boundary conditions. But in this case, the mesoscale model does not inherit any boundary condition from the global problem. So we have no boundary conditions in this case. So the next step is to go back to the assembly module. No, sorry, the next step is to create a mesh. And again, the user must guarantee that the mesoscale model has a single solid element at the global meso interface. So we can enforce a 1-to-2 correspondence between the global and mesoscale nodes along the interface. So if this is the global model, and on the left we have the mesoscale model, there is a single element at the global meso interface, and there is a 1-to-2 correspondence, one node from the global model and 2 nodes from the mesoscale model. So let's mesh our mesoscale model. We have one element through the thickness. Let's go to mesh. Let's assign the element type. Uncheck reduce integration linear. So we will use a C3 E8 element. Click OK. And now let's create the mesh. Let's click on seed edges. And all these edges have a single element through the thickness by number 1. OK. Here we have 2 elements here, the same here, here, and here. So we have 2 elements here, 2 elements here. Also here and here. Click done by number 2 and click OK. And also we have 2 elements along this edge. Select the edges. Done. 2, okay. And now we can mesh the part. We are missing one edge, which is this one. And here we have 15 elements. So let's see those edges with 15 elements. Click OK. And now let's mesh the part. And as you can see, we have the same mesh as in the tutorial. So the next step is go back to the assembly module and select all the mesoscale elements that are at the global meso interface and create an element set with the name global interface element. So let's go back to this model, to the assembly module. Let's show the mesh. Tools, set, create, element. Let's use this name, continue, and select all these elements. Click done. And select all the mesoscale nodes that lie at the global meso interface and create a node set with the name glob interface node. So again, let's go to the assembly module, tools, set, create. This is a node set with this name and click continue. Select all these nodes and click done. Finally, we have to create the job and perform a data check. So let's do it. Let's go to job, create job. Let's call it meso solid, continue. Okay, let's go to the left menu, right click on the job name and data check. So the check has completed successfully. So we can write the input file, right click on the job name and click on write input. And the job input file has been written to this file. So if we go back to our work directory, we have the Abaqus input file of the mesoscale problem. Finally, the local model for an IGL-GFEM simulation, the local problem is created automatically and it is defined by the set of mesoscale elements that lie inside a user-defined bounding box. However, the user could also create the local model using Abaqus, following the same guidelines as for the mesoscale model. However, in this case, the user must guarantee that the local mesh is nested in the mesoscale mesh.
Let's continue with our IGL-GFEM simulation with shell solid coupling between the global and mesoscale problem. So now we will do the Abaqus to ISET conversion. The steps to convert an Abaqus input file into ISET format are the following. First, if the Abaqus input file was generated in Windows, we recommend copy and paste the content of the input file to a new file with the same extension .imp. This is needed to delete any special character that might have been generated and might cause troubles during the conversion. I already did it, these are the two original global, shell, and meso-solid input files. I created a new file with the same extension, and then I copy and pasted all the content. And I repeated the process for the meso-solid case. Then verify that the Abaqus to ISET converter and the Abaqus input file are located in the same directory. So first, let's do the conversion of the global model. Both files are here. So let's open a terminal window and execute the converter. Let's follow the instructions. Since our global model is made of shell elements, we have to select option 9. And then provide the name of the input file. And then press enter. We will get a warning message indicating that ISET shells only handles point loads. So if in the Abaqus input file, we prescribe other type of loads, such as edge shell loads, those will be ignored during the Abaqus to ISET translation. However, we used point loads in the Abaqus file, so we are fine. Two files have been generated. The first one is this one with extension GRF, which is the shell global model in ISET format. And this one, IGL.imp, is a clean version of the Abaqus global shell input file. So let's rename this file global mesh. And let's rename this file. Now let's repeat the process with the meso mesh. Both files are in the same directory. Open a terminal window, execute the converter, and follow the instructions. In this case, our mesoscale model is made of hex 8 elements, so we have to choose option 3. And then provide the name of the input file. And press enter. We have no errors. The process is done. And two files have been generated. This one with extension GRF, which is the solid mesoscale model in ISET format. And this one is a clean version of the Abaqus mesoscale solid input file. Let's rename this one. And since we do not run the mesoscale model using Abaqus, we can leave this file as it is. Now let's proceed with the node equivalence. During an IGL-GFEM GL simulation, there is an interchange of nodal information between the global and mesoscale model along the global meso interface. So for the case of a shell solid coupling, we need a 1-to-2 map between the global and mesoscale nodes respectively. So the steps to generate this node equivalence between the two models are: verify that the Abaqus to ISET converter and the Abaqus global and mesoscale input files are located in the same directory. So both input files are here, and we also have the converter. Let's open a terminal window, execute the converter, and follow the instructions. In this case, we are doing a shell solid coupling or shell solid node equivalence. So we have to choose option 11 and provide the name of the input files. We press enter. We have no errors. The process is done. And the following files have been generated. The first one is this interface resforce.lod. And this file contains concentrated forces applied at the interface nodes of the global model. It is worth noting that this file is used only when the global problem is solved using Abaqus and has the following format. This is the global node ID, DOF, and the value. The next file is node equivalent append to global. And this file contains the node equivalence information in the following format. For a shell solid coupling, this is the format of the file. And finally, we have this node equiv append to lock. And this file contains node equivalence information in the following format. For a shell solid coupling scheme, this is the format. Okay, now, depending on the type of IGL-GFEM GL simulation, the content of these last two files should be used as follows. For an IGL-GFEM GL simulation where both global and mesoscale models are solved using ISET, open node equiv append to lock to glove and append its content to the end of the converted global model in GRF format. So let's open this file. Let's copy the content. Let's go back to the global model, the converted global model. And paste. Click on save. Then open node equiv append to lock txt and append its content to the end of the converted mesoscale model in GRF format. Let's open append to lock. Let's copy the content. Let's go back to the converted meso model and paste. Click on save. There are additional steps that we have to do, especially in the meso mesh. So we have to copy and paste some boundary conditions that will be used for the local problem. So let's copy these boundary conditions and let's go to begin boundary. And paste. Click on save. Also, if we have boundary conditions in the meso mesh that were inherited from the global problem, we have to do an additional process, which is detailed here. But in the case of a shell solid coupling, the meso mesh does not inherit boundary conditions, so we are fine. And this finishes the conversion of the files. Let's continue with the IGL-GFEM GL simulation files for a shell solid coupling between the global and mesoscale problem. The following file names are suggested and are the ones used in this tutorial. However, other file names can be used by changing the input file names in the TCL files and Python scripts. Let's start with an ISET simulation. Running an IGL-GFEM GL simulation where both global and mesoscale models are solved using ISET requires 5 files. We need an IGL simulation.tcl, and this file is the simulation driver, which is passed on the command line to the ISET executable. We also need IGL simulation glove.tcl, and this file runs the global shell model with a given residual force. We also need global mesh.grf, which is the global shell mesh in ISET format, and this file was supplied by the converter. We need mesomesh.grf, which is the mesoscale solid mesh in ISET format. Again, this file was supplied by the converter. And since we are running a fracture simulation, we need a crack.crf, which is the crack surface representation in ISET format. Some of these files may need modification before running the IGL-GFEM simulation. For instance, we may need to modify IGL simulation.tcl and prescribe different parameters, such as the number of IGL iterations, polynomial order of the approximation space, bounding box coordinates used to define the local problem, etc. So these are the files that we need, and we may need to modify this one. As you can see, we have some input parameters, name of the files, polynomial order, iterations, tolerance, bounding box coordinates used to define the local problem, etc. So I recommend reading this file to have a better understanding of how the IGL algorithm works. Then we may need to modify IGL simulation glob.tcl, because here we use a bounding box to define the global meso interface. Here, and the input parameters are defined here. Then we also may need to modify global mesh.grf, because as stated in previous sections, the node equivalence must be appended to the end of this grf file. So let's check global mesh. This global mesh is made of shell elements, and the node equivalence information is already here, because we did it in a previous step. Then we may need to modify mesomesh.grf, because we have to include the node equivalence at the end of the file. And also we have to include the boundary conditions that can be used by the local problem, these boundary conditions. So let's check if everything is in place. Let's open mesomesh. The node equivalence info is here. And also the boundary conditions for the local problem are here, because we did it in a previous step. Now let's go through the Abaqus ISET simulation. The steps outlined here are for running Abaqus in a remote machine or simply in another folder of the same machine. Running an Abaqus ISET IGL-GFEM simulation where the global model is solved using Abaqus while the mesoscale model is solved using ISET requires 10 files in the directory where the Abaqus global model is run and 4 files in the directory where the ISET mesoscale model is run. In the folder where ISET will be run, these are the files that we need. Let's go to Abaqus ISET, and these are the files that we need. So we need an IGL simulation.tcl, which drives the simulation. We need a mesomesh.grf, which is the mesoscale solid mesh in ISET format. This file was supplied by the converter. Since we are solving a fracture problem in this case, we need a crack.crf file, which is the crack surface representation in ISET format. And we need an ISET to abaqus.py which is a Python script that converts interface residual force from ISET to Abaqus. Then in the folder where Abaqus will be run, we need these files. This is the folder where Abaqus will be run. And we need all of these files. The first one is the Abaqus input file of the shell global model. And again, was generated by the converter. We need an interface resforce.load, which is the nodal loads in Abaqus format. Again, this was generated by the converter. And we need some additional files. Some of these files may need modification before running the IGL-GFEM simulation. For instance, we may need to modify the IGL simulation.tcl because we need to provide some information about the machine where we will run Abaqus. For instance, I need to specify my password, the IP address of the workstation, and the path of the folder where I will run Abaqus. Then I could also provide the name of the files, the polynomial order of the approximation space, number of iterations, tolerance, bounding box coordinates, and etc. We may need to modify mesomesh.grf because, as stated in previous sections, we have to include the node equivalence, and we also have to include these boundary conditions that will be used by the local problem. So let's check. The node equivalence is here. And the boundary conditions for the local problem are also here. So everything is in place. Then we could also have to modify this file and set the type of license of the Abaqus software. And then we could also need to modify this file and provide the Abaqus job name and some other information. But this concludes this step of the tutorial. Let's continue with the solution of the T-joint using IGL-GFEM with shell solid coupling. First, we will use an ISET simulation. It is worth noting that we will use a staggered scheme, which is presented in this algorithm. So first, create a folder with this name and copy all the necessary files that are needed to run an IGL-GFEM simulation with shell solid coupling described in this section. We also need a symbolic link to the ISET executable. Then open IGL simulation.tcl and check that you are using the same value for these parameters. The approximation space is 2, maximum number of IGL iterations 30. This is the tolerance value, and 1 global local iteration. So let's open IGL simulation.tcl. Let's check that we are using 2 as the polynomial order, 1 global local iteration, 30 as the maximum number of IGL iterations, the tolerance value. So everything is correct. Now solve the problem with ISET using the following command. So let's go back to the folder. Let's open a terminal window and use this command. So we will be running the IGL simulation.tcl, and all the output information will be written in this file. So press enter. And now we are running an IGL-GFEM simulation. So after the simulation is done, we will use several files. So these are the files that are ISET generated, but we will use only a few of them in this tutorial. The first one is out.txt, which contains the norm of the residual forces at the global meso interface. We will also use IGL simulation.cm-SIF, which has the stress intensity factors along the crack front. We will use IGL simulation glove.btu, which has the solution of the global problem. IGL simulation ITER1EG, which has the solution of the enriched mesoscale problem. And IGL simulation ITER1LOC, which has the solution of the local problem. So first, let's check the relative norm residual. So let's open out.txt and search for relative norm residual. And then you will have to plot these values in the y coordinate and the iteration number in the x coordinate, and you should get something similar to this plot. Then we will check the solution of the problem, of the global problem, as well as the mesoscale problem. So if you follow these instructions, you should get a deformed configuration of the global problem and enriched mesoscale problem similar to this one. So I already did it with the new files. And as you can see, the deformed configuration is pretty similar. And the value of the solution y is also similar to the one which is shown in the tutorial. Then we will have to follow all these instructions to show the bone misses stress in the mesoscale problem. I already did it. And as you can see, we have a stress concentration near the crack tip and also here, which is similar to what is shown in the tutorial. Finally, we will plot the stress intensity factors along the crack front. So you will have to use this file, all the info that is in this file, the 3 stress intensity factors, and plot them. If your plot is similar to this one, we can say that your IGL simulation, IGL-GFEM simulation is correct. Now let's continue with the second part of the solution of the T-joint using IGL-GFEM with shell solid coupling. In this case, we will use an Abaqus ISET simulation. So let's scroll down and we have the Abaqus ISET simulation. We should note that this simulation will use a staggered scheme, which is presented in this algorithm. First, we will have to go to the folder where Abaqus will run and check that all the necessary files described in this section are present. So I'll be running Abaqus in the workstation, and this is the folder that I created. And as you can see, I have all the necessary files to run the IGL-GFEM simulation using Abaqus ISET. So then create a folder with this name and copy all the necessary files that are needed to run IGL-GFEM simulation described in this section, and also a symbolic link to the ISET executable. I already did it. I created this folder in my local machine. And also I need to copy the ISET executable, a soft link to the ISET executable. So all the files are ready. Then let's check that we are using the correct parameters, as you can see here. So let's open IGL simulation.tcl and check the polynomial order of the approximation space, the maximum number of IGL iterations, the tolerance values, and the global local iterations. So let's open IGL simulation.tcl. We are using polynomial order equals 2 for both problems. That's correct. 1 as the global local iterations, 30 as the maximum number of IGL iterations, and the tolerance value is correct. So we are ready to run the problem. So in the folder that we just created in the local machine, let's open a terminal window and execute the simulation using this command. And then we press enter and we will execute the IGL simulation.tcl and send all the output to this file. Once the simulation is done, we will have several files that ISET generated. These are the files that ISET generated, but only a few of them are particularly useful to us. The out.txt, which has the norm of the residual forces of the global meso interface at each IGL iteration. IGL simulation.cm SIF, which has the stress intensity factors along the crack front. IGL simulation iteration 1 EG, which has the solution of the enriched mesoscale problem, and IGL simulation iter 1 loc, which has the solution of the local problem. At this point, it is worth mentioning that we also need to download the folder where we run Abaqus, because it also has some useful information. But at this point, we do not support the conversion of Abaqus output files to ParaView format. So we will have to use a quick around in order to show the deformed configuration of the Abaqus solid problem. But in the meantime, let's continue with the tutorial. So let's open out TXT and search for relative norm residual. So let's open out.txt. And we will have to plot this value in the Y coordinate and the iteration number in the X coordinate. And you should get a plot similar to this one. Then we will check the solution of the global problem. However, as I mentioned before, we will have to use a workaround to display the deformed configuration of the Abaqus global model. And we will show this procedure in a future video. So let's continue with the tutorial. So we will have to show the enriched mesoscale problem using ParaView and study the results from the simulation. So if you follow these instructions, you will get the deformed configuration of the enriched mesoscale problem, which should look similar to this one. I already did it here. And as you can see, the deformed configuration of the mesoscale is similar to the one shown in the tutorial. Then, if you use these instructions, you will be able to show the von Mises stress at the enriched mesoscale problem and should look similar to this one. And again, I already did it to save some time. And as you can see, we have a stress concentration near the crack tip and here, which is the same behavior that we have in the tutorial. Finally, you will have to plot the stress intensity factors along the crack front, and you can find the value of the stress intensity factors in this file with extension SIF. So you will have to plot the 3 of them, and you should get a plot similar to this one. So these are the checks that you will have to do in order to check if your IGL-GFEM GL simulation is correct. Now let's go through the Abaqus global model post-processing for an IGL-GFEM GL simulation with shell solid coupling between the global and mesoscale problem. If an IGL-GFEM GL simulation uses Abaqus to solve the global model, there is no conversion of the abaqus.odb file to ParaView format. So in order to visualize the solution of the global model, we need a modified version of the Abaqus input file and the final version of interface resforce.load. The process is detailed as follows. So first, create a copy of the Abaqus global model.imp that was used in the IGL-GFEM GL simulation and rename this file as IGL simulation glob post. So first, let's go to the folder. This is the file that was used in the IGL-GFEM GL simulation with Abaqus ISET coupling. And this is the final version of interface resforce.load. So let's create a copy of this file and let's rename the file. Then use a text editor to open this file and search for include input interface resforce. Delete everything after this line, but excluding end step, and then copy and paste the following code. So let's copy the code. Let's open this file. Let's search for include input interface resforce. Delete everything after this line, but excluding end step. And finally, paste this code. Click on save and close. So this code requests as output the displacement field and the bond misses stress. So please refer to the Abaqus manual if other quantities are needed. Now let's open Abaqus and set the working directory. Let's open Abaqus, file, set work directory. Okay. And then in the job module, create a new job, specify a job name. In the source tab, choose input file and select this file. So let's go to the job module. Let's create a new job. Let's call it post global shell. Let's choose input file and select the file. Click OK, continue, and OK. In the left menu, let's go to jobs, right click on the job name and click on submit. The simulation has finished. We got a message saying that the job has completed successfully. So if there are no errors, you should get this message, as I mentioned before. Then right click on the job name and click on results. Right click on the job name and click on results. And now we can use the visualization module to show the deformed configuration of the Abaqus global model. So let's select plot contours on deformed shape. Let's choose U and U2. And now let's compare if we have the same result as in the tutorial. So if we scroll down, we have the reference solution here. The deformed configuration looks pretty similar. and the maximum value is 4.9 times 10 to the negative 1, which is the same one that we got here. So in this way, we have checked the solution of the Abaqus global model.